So let's start today's session. Hi all, welcome to the session on feature engineering. So my name is Shubhangi and along with me Vaishakhi is there who will be helping us in understanding the today's agenda. Okay. So basically today the session is specifically organized on outliers, right? And basically we will be understanding what are the causes of outliers, okay, how outlier impacts the ML algorithm, and what are the ways or what are the steps to handle the outlier, and then we will jump for the Python implementation part. Okay, so let's get started. So I hope everybody present in this webinar may have at least a little knowledge on outliers, right? So we'll start with a very scratch definition of outlier. That is, it is an observation that is unlike the other observation. Okay, so and mostly it is rare, distinct, and does not fit in some way. So basically, we are talking about that kind of observations which are very different from the usual observations. Okay, so when modeling, it is important to clean the data sample to ensure that the sample best represents the population. Okay, and if we have samples which have different characteristics from the normal observations, then it becomes difficult for machine learning algorithms to understand the pattern hidden inside the data. Okay, so this is what an outlier means to a machine learning with respect to machine learning. Okay, so we will generally define outlier as samples that are exceptionally far from the mainstream of the data. Okay, so this is what we try to understand as a outlier. So if you can see this image, so certain population we have over here or certain observations we have over here. But if you could see here, 1, 2, 3, these 4 people are quite away from this people. Okay, right? So just in a diagrammatically, we can say these are the outliers. Okay, so now we will understand what are the causes of outliers. So causes of outlier, basically data entry error. So usually the data collection steps which involves human, right? Certain Google forms, certain data entry applications, right? May possible while entering the data we are making mistakes. So that mistakes are accountable for getting outliers in the collection of the data. Okay, even the instruments that are getting used, they can also insert some of the outliers in the data, right? Then experimental errors, right? So when we are doing certain kinds of experiment, right? So that time also while taking down the observations, right? So that can also insert outliers in the data. In some of the processes, okay, specific to the machine learning part, what we do, we try to insert dummy outliers to test whether our model is robust to outliers or not. Okay, so this is another way in which we intentionally add outliers to a data, and that data has been will be provided to the algorithm. Okay, then data processing error, that is specifically the data pre-processing error, right? If you don't do data pre-processing, that means the handling of missing values, right? So basically what happens is that this kind of processes also insert error or basically the outlier in the data. Okay, sampling error, right? So basically sampling error says that getting data from wrong sources. Okay, this is the major challenge those who are involved in data collection, specifically to the projects which are towards the research. They need to collect exact data. Okay, so if the data collection is done from a wrong source, So again, we are giving a outlier to the algorithm, and we are expecting to do some problem which for which the data has been not supplied, some other data has been supplied, right? So sampling error introduces outlier in this way. And most importantly, the natural, okay, or we called as novelties in the data, right? So if you take credit card transactions, okay, so out of that, let's assume in a daily basis a bank is doing 1 million of transaction, okay. Out of that, may possible we can have one or two fraud transaction, okay. So this kind of imbalance, okay, is called as novelties in the data, and they are also the outliers. However, they represents the property of domain, okay. And right, so these are the possible causes by which outliers are introduced in the data. Now, okay, so these are the causes, but why ML algorithm should be worried about the outliers? Okay, so basically, it does, outlier shifts the target equation. So target equation is that equation which is created by machine learning, any machine learning algorithm, by checking on the pattern, right? If the pattern itself has an outlier, so the original target equation, basically we won't able to capture the real relationship between the variables, okay, making algorithms to predict some different results. And specifically we call this, whenever there is a shift in the target equation, we called it as a bad prediction, okay. So this is how the outlier impacts the machine learning, okay. And the severely affected algorithms are those algorithms which uses distance, right, like linear regression, logistic regression, knn, svm, k-means. These are the algorithms which are severely affected by outliers. So whenever we are applying all these algorithms, we have to be super careful to handle them, to handle the outlier, okay. However, the tree-based algorithms like decision tree, random forest, XGBoost, okay, gradient boosting, this all are robust to outliers, right? So basically, they are built on a decision tree. Decision tree is nothing but a simple nested if-else condition only, right? So because of this target nature, the tree-based algorithms are robust to outlier, okay. But yes, when it comes to the algorithm which uses distance, we have to be super careful, and it's mandatory to handle the outliers, okay. So till this part, if you have any questions, you can put it in QA section. I'll try to answer them. Now let's see how to handle the outliers, okay. So the first step in any whenever we start with any algorithm, okay, so basically outlier handling is a step of data pre-processing, okay. So in data pre-processing, the first step in outlier is to visualize the outlier, okay. So visualization is usually done by scatter plot or box plot, okay. You can use any of the method, but it is highly recommended to use box plot for the visualization of outlier, okay. Once you have visualized the outlier, the next step that you have to remember is 5% rule. What does this 5% rule means? So a 5% rule is that you need to get the upper limit and get the lower limit, okay, and then calculate how much percentage of the data is outlier, okay. If the percentage of data outlier is greater than 5, you should not handle the outliers, they should kept as is, okay. Means no techniques has to be applied on them. Why? Because they are again representing a certain combination, even though they are unusual from the regular expression, regular samples, but excuse me, sorry for that, yeah, but they are representing certain other pattern in the data, right, and they are in the huge number, so that is why we are limiting the outliers to 5%. Okay, so if you have outliers greater than 5%, do not impute it, okay, or do not handle them. But yes, when it is less than 5%, the first option is to do the imputation, and then the last option would be dropping them. The last, never ever drop. So basically, it's a thumb rule in a feature engineering. Whenever we fix the features or whenever we fix the data, first do imputation, okay, and then the next step should be dropping it. If you drop the data, what will happen? We will lose the information. Okay, so this is what we try to do in a 5% rule. And then, yes, as I said, applying imputation method. So this imputation methods will be discussed by Vaishaki with Python implementation, and she will give you a good walkthrough on the code as well as which technique to use when. Okay. So this was a little bit introduction about outliers in machine learning algorithms. Now I will hand over the session to Vaishaki to start over the imputation methods.
Thank you, Shubhangi. Thank you for this information. And hello, everyone. Good morning to this session. We'll be starting with a basic introduction about outliers first. And we'll also see a bit into detail about how they affect the machine learning and how we can identify them, basically how we can identify and visualize outliers also. And we will discuss about the different techniques through which we can handle them. And we will also go through the Python implementation by one, code by code. I'll explain you that how we can actually detect them and how we can also handle them. Shubhangi, can you please let me?
Yeah, sure, you can share your screen.
Well, we've already, Shubhangi has already discussed about what outliers are. So I would like to start with, should outliers be removed? Well, it depends on the context. So outliers, they either deserve a special attention, as she said that if we have around outliers present in more than 5% of the data, then certainly there is a reason that they are present in the data set. So outliers are either they deserve that kind of special attention or they should be completely ignored. Because the thing is that, let's say the example of revenue forecasting. If you see the unusual spikes of revenue are observed, so it is probably a good idea to pay extra attention and try and figure out what causes that spike. Or in the same way, if an unusual transaction on a credit card is appearing, so we may want to have a deeper look at it because it may be a sign of a fraudulent activity. Certainly, if you see higher amount of transactions happening, so certainly it's a fraudulent activity, and that is what our focus point should be. Instead of handling those higher transactions, we should be more focusing on them. So in these kind of instances, it is useful to look for and investigate further those outliers. But if outliers are, however, introduced by any mechanical error or measurements error or anything or any other reason that can be generalized, so it's a good idea to filter out those outliers, because feeding that kind of outliers into a model algorithm would not give us a very good prediction to us, right? Next is how they affect different kinds of algorithms. So we have already seen how it affects linear models. We have already discussed that how outliers affect the best fit line, because of the outliers, the cost function of the linear model gets affected and it does not converge to the optimized solution that easily, because the distance from the best fit line certainly is very high when it comes to outliers. In case of AdaBoost, which is one of the tree-based algorithm, the information that is passed from the different estimators is weights. So what happens in AdaBoost, they are very sensitive to outliers because it puts tremendous, the AdaBoost, it puts tremendous weights to the outliers as the different trees are built to try and correct the wrong predictions made by the previous tree. And therefore, this causes overfitting and then generalization issues also for those extreme values. When it comes to tree-based algorithms, certainly they tend to be quite robust to outliers. So in whether we are using linear models or even if we are going for tree-based models, yes, if we are going for other models except AdaBoost, we needn't put up a lot of focus into handling them. But if we are going for linear models or AdaBoost, then we'll have to handle these outliers. First, we'll see what are the different techniques, what are the different ways through which we can detect these outliers. So the first method is if you have a normal distribution, if the variable has is normally distributed, we can use the empirical rule, that is mean plus minus 3 into the standard deviation rule to detect them. If otherwise, if the variable is not normally distributed, we can use some other techniques such as interquartile range proximity rule. Okay, and we can also detect outliers using quantiles method. Let's see them one by one. In case of normal distribution, as we know that around 99.7% of the observations of a normally distributed variable, if you see from here in this plot, they lie within the mean plus minus 3 standard deviation. So if you see here, zero is representing the middle of the distribution and also mean because this is a normal distribution. And if you see plus minus 3 standard deviation, that this is from this range to this range is where 99.7% of our data lies. Okay. And any point lying beyond this range can be considered as an outlier. So we can use a capping technique to put a cap. If we are not going for trimming, that is removing them, we can cap them. This is a technique that we'll discuss later, but this method is how you can detect outliers in your data set when it comes to normally distributed data. What happens if your data is not normally distributed? If something that we have going for skewed data, or if the data is skewed in terms of distribution, then we can use something called as an interquartile range approximation rule. The general approach is to calculate the quartiles first and then the interquartile range, and then we can apply this formula over here. That is, we can count the upper limit and lower limit. So first we calculate the interquartile range. So interquartile range is the difference between the 75th percentile, okay, and the 25th percentile. So 75th percentile is also called as the third quartile, and 25th is also called as the first quartile. So once we calculate the difference between the these quartiles, that is IQR we get, then we can calculate the IQR range, that is interquartile range from that. And then we have to find the limits beyond which a value can be considered as an outlier. So these are the limit. The upper limit for that would be represented by the 75th quartile plus the IQR that we calculated before into 1.5. And the lower limit similarly will be counted by taking into consideration the first quartile or the 25th quantile minus IQR into 1.5. That is the formula through which we can get the upper limit and the lower limit. And once we get this, so any value which is present beyond upper limit and lower limit will be considered as an outlier. Okay. When we have extreme outlier cases, we can replace these values with 3 also. But usually we take 1.5. If we are only targeting for extreme outliers, then we can multiply it by 3 as well. Okay. The third method is using quantiles. So here we will consider any value which is present before the 5th quantile in the distribution and beyond the 95th quantile in the distribution. So those will be considered as outliers, and those can be handled because when it comes to quantile method, we can also change this 5th quantile to 2nd quantile as per our choice. If we are taking 5th to 95th quantile, which means that we are covering up the 95% of the observation within this, and any observation beyond it would be removed. If we are taking into consideration 2nd to 98th, then around 98% of the observation will be covered up, and any observation present beyond it would be considered as an outlier and can be handled accordingly. So these three techniques are there which can help us detect outliers in our data. Any questions till now? Okay, let's go and see how we can visualize these outliers. So the best way to visualize outliers is using box plots. Okay, so in this, this is a simple representation of how a box plot looks like, and let's see what all of these uh, information tells us about. So if you see this, the box in this plot, it represents the interquartile range. If you see over here, the bottom line is representing the first quartile, and this, the top of the box, is represented by the third quartile. Okay, and this box tells us about the interquartile range, and which is also where the 50% of the observations are found. Okay, if you see this line, which usually lies in the middle, but if it's not, it's okay. But this line is representing the median of the data set. Okay, and if you see the edges of the box, that is the first and the third quartile. Okay, what is the first and the third quartile? What does it represent? It represents, the first quartile represents around the 25th percentile of the data, which means that this is the point, or here is where the 25% of our data lies. From starting to this point, around 25% of our data lies. That is called as the first quartile. So this is probably where the first quartile of our data lies. The third quartile, that is also called as the 75th percentile, it is represented by this point. If you see, this is the third quartile, and this is represented at this point here in our distribution, is where around 75% of our data lies. Okay, and the difference between both these quartiles is represented as IQR, which is called as interquartile range. So based on this interquartile range, we calculate something called as a maximum and minimum, okay, which is the mean plus minus 3 standard deviation, is how we also can calculate the maximum and minimum from this box plot. So around 99% of our observations are contained within the limits of this whiskers, okay. And the limits of the whiskers, they coincide more or less with the mean plus minus 3 standard deviation, or we can say upper limit plus minus RQR into 1.5. That kind of a estimate we are able to get from this. Okay. So for normal distribution, we can also use the IQR proximity, as it is called, to identify outliers. So any point which lies beyond this upper limit or beyond this whisker is called as an outlier. And any point which lies below this whisker will be also identified as an outlier only. Okay. Any questions here? Fine, let's move ahead. So what are the different ways through which we can engineer these outliers? What are the different ways through which we can handle them? So one method is either we can just remove them from the data set. That is also called as trimming method. But as suggested previously, if they are present in lesser amount, or it is due to only some measuramental errors, let's say if we are present less than 5% of our data, then we can go for trimming method if we are okay to removing them. And if they are not there, if they are not present there and giving us a valuable information about the predictors, about the target variable, then we can go for trimming also. But if the reason for their presence is, if the percentage of the presence is more than 5%, then we should not remove them. Let's say that we should use some other technique. So for that, we can use capping technique also. So capping is any value which is present beyond a certain upper and lower limit, they will be automatically replaced by the upper and lower limit. That is called as capping. Okay. So the first way, the trimming, it involves removing the outliers straight away from the data set. So imagine if you have around more than 5% of our data present as outliers, if you are removing them completely, so you're losing out on a lot of information. So this is not very much suggested because outliers are rare in theory, and we shouldn't be removing a lot of data when we apply this technique. In case of capping technique, any value that is smaller or bigger than the caps will be replaced by the capped value. Okay. But as we say that both these techniques have some advantages and they also have some disadvantages. When it comes to trimming, as we have already discussed, the major advantage of trimming is that it is very fast. Okay, this method is very fast. We are just removing them from the data set. That's it. And the major disadvantage of this data is that it removes a big chunk of data from our data set. We may end up removing a big proportion of the data, and that proportion may also be helpful in predicting or in at least helping us to predict the values for the target. If we go for capping method, it also has certain pros and cons. The advantage over here is that there is no data being removed. Okay, so we are having all the information intact. It's only that the outliers values are getting capped a bit below or a bit above as per which location they are present at. And it is also very fast. But the major drawback is that it affects the distribution of the data. So this technique, it distorts the variable distribution, then also distort the relationship of this variable with other variables in the data set. So if you are going to use it for linear regression, we have to handle them very carefully, because in using linear models, we have to make sure that the distribution of data has to be kept intact. It should not be distorted to beyond a certain limit. So we have to take very capping also we have to take into consideration very carefully. Okay. So we today in this session, we will be discussing trimming and capping, both these techniques along with the Python implementation. So let's move to that. But till now, if you have any questions, please ask. Any questions in any topic? Yes, Sapna? Yes. What about skewness? In case of skewed data, how to handle that or how to detect that? If you have a skewed data set, then to detect it, we can use the interquartile range proximity rule while you're computing the value of skewness. So certainly if you're computing the skewness value, you will be doing it to understand whether the variable is normally distributed or not. From that, you get that information, right? So if it is normally distributed, you can use any method to detect the outliers. But if you see that the distribution is slightly skewed, then you can go for interquartile range proximity rule. It helps us to detect outliers.
Vaishaki, there is one question from anonymous attendee, so let me take that. So the question here is from box plot, how to know the amount outliers more than 5%. So basically the steps right now Vaishaki told, right? After visualization, then we will be calculating the upper limit and lower limit, right? Then using log and ilog function, you need to filter the data, and then simply using length and percentage formula, you can get the actual data which is outlier. Okay, so simple mathematics you have to apply. Over to you, Vaishaki.
Yes, Sapna also asked about after computing skewness also, we need to do interquartile range. Skewness is a parameter which tells you about the distribution of your data, whether it is skewed, it is distorted, or it is normally distributed, right? When you have to detect outliers, then for that we have to use the RQR technique, the rule for that. The skewness and RQR range are completely two different parameters. They are detecting two different things about a distribution. So I have a question from Rohan as well. What is the difference between quartiles and quantiles? Quantiles is when you divide your data set into equal number of intervals. and every interval is called as a quantile. When you're talking about quartile is when you take the first 25th quantiles. That is one quartile. Quartile is like dividing your data into 4 equal parts, and every part is called as a quartile. But when you divide your data set into n number of equal parts, and every part is called as a quantile. So we can say a quartile is like a subset of a quantile. Percentile can also be called as a quantile. Quartiles can also be called as a quantile. Okay. In percentile, we are dividing our data into 100 equal parts. That is a special kind of a quantile. Similarly, in quartile, we are dividing our data into 4 equal parts. So that is a special kind of a quantile. Okay. So quartiles and percentile, they come under quantiles. Okay. Is this clear, Rohan? Thieneshwaran, skewness also represents outliers. Well, one of the reasons why skewness is present in the distribution is outliers. Yes. So if your data is skewed, then certainly some outliers are present. Any other questions? Okay. Okay. Someshwar is asking when to use the 3 sigma, the empirical rule, or when to use the RQR rule. If you see the 3 sigma and the empirical rule, we can use in case of normal distribution. Okay. When it comes to if you have skewed data set, then you can use the interquartile range proximity rule. So you'll have to check for the distribution of the data first. Yes, Manoj, we'll have to check the distribution of data. Then only we'll be able to understand which technique should we go for in detecting outliers. When it comes to distribution of data and when you're specifically using for linear or any distance-based algorithms, checking the distribution of your continuous variables is always a must. Even before using any technique and after using also, we have to check how it has impacted it, because we have to be very careful when it comes to linear models. No, Thieshna, it is not the case like that. It's just the 2 different techniques that we can use for 2 different kinds of distributions. Both of them will represent the outliers. Okay. As it says that, Manoj, it depends. It depends on what kind of data you have and what exactly is the information that you have been checking for, what variable were you checking for. So we'll have to see through it and then we'll be able to answer this question, Manoj. I think yes, you just need to raise your hand. Thieneshwaran. Shubhangi, I think you'll have to do that.
Yeah, I'll do this.
Hello, ma'am.
Hello.
Myself, Dhyaneswaran. Actually, I have doubt in the capping process. Like, if I have a variable which has a count of around 2 lakhs, but the normal distribution count is around 50,000 or 60,000, then it may represent like 1,40,000 as outliers. If I do capping to the minimum value or maximum value, then the most of the values like 1,40,000 will be in that range, like within either in the minimum or in the maximum. So when I do my modeling, then what can happen is that it may overfit my data. Like since here the data are duplicated, the values are duplicated, then there may be a chance that it may get overfitted. Like, is there a chance in this process, like it may overfit in this case?
So what is the variable that you're talking about? What is it?
Actually, yeah, variable, whatever. Like in case of fraud detection, you can say like in minority class we have 500 variables, and in majority class we have around 2 lakh variables, and I have 20 predictors, and each predictor has around 2,50,000 samples or values.
If you're talking about transaction of money, and if you are talking about that specific variable, then I don't think that my approach, I'm telling about what I would do, is I would keep them, because
Yeah.
they are the ones that will also help me predicting whether it's a fraudulent transaction or not.
Okay, then we should not treat it as an outlier, and we should not do any removing capping and all like that.
One of the approach can be that. And in case of those fraudulent, then it certainly wouldn't be a regression analysis, it would be a classification. So you can go and use for tree-based algorithms because they are unaffected by outliers. So you can use them.
Directly, I can use it in a tree-based algorithm.
Yes.
Okay, ma'am. Okay, thank you, ma'am. That's it.
Tanish, you're adding to Vaishaki, you need to balance the data as well. Means you need to perform
Is
balancing as well.
like 0 mean and standard deviation to 1.
No. Balancing means basically your smart techniques, right? You have to
Yeah,
apply
yeah, yeah.
certain smart as well.
Ma'am, actually, I have one doubt over there.
Mhm.
In smart techniques, like if I do balancing of my minority class, anyway, the samples are being generated synthetically, but it tends to overfit sometimes. Like if we compare it with oversampler and smart, oversample definitely it will overfit, but even if the smart synthesizes the data synthetically, there are cases the model overfits my entire model. For example, what I have shown in classification problem of fraud index, and I have majority class of around 2 lakh data and minority class of around 500. So
Mhm.
if I like balance that, my 500 minority class has to bring it to around 2 lakh. I have to balance it with my majority class. In that case, so even if I get 99% of accuracy in classification, does it mean that my model hasn't overfit the data?
No,
So
when
how?
you are solving classification task accuracy, you should never check. You should go either for recall or
Yeah, yeah,
precision.
yeah. I checked recall as well, precision and recall as well. Why without balancing, I get something around 0.7 and all. After balancing, I'm not balancing to the entire range, but I maintain a sampling strategy, some ratio. I'm maintaining like 1:10 ratio or 1:5 ratio between my majority and minority. So in that case, I get a higher recall of around 0.9 to 0.95 and all. So is it valid that my model hasn't overfit my data? How can I check
Yes.
that?
Yeah, I think the model is performing good, but you can check cross validation score as well for that. Okay.
Okay, ma'am.
Okay.
Okay, ma'am. Okay, ma'am. Thank you very much, ma'am.
Also, one of the major techniques to reduce overfitting as much as possible is to always perform the analysis of feature engineering in your training set only, and separating the data into training and testing and not applying it with respect to testing. Keep the testing aside, only apply engineering to training set. That will also try to handle overfitting to a very huge extent, whether it is in the case of missing values handling or it in case of outliers handling also.
Okay, so I should not keep do feature engineering in terms. What are all the techniques you are mentioning, ma'am?
So split your data set first and then apply for feature engineering only with respect to the training data set.
Okay, ma'am. So I should keep aside my test data. Don't do anything
So
except
so you can apply the technique
na-
on the complete data set, but when it comes to detecting them, then you should split first.
okay, so smart and all I should not do with my test data.
Smart technique, you apply it on the training data, right?
Yeah, training data. I actually did smart on the entire data set.
Okay, so try splitting it first and then apply sport analysis only to the training data.
Okay, ma'am. So I can have my test data as a new one.
Yes.
Okay, ma'am. Okay. Thank you, ma'am.
Any other queries, guys? Okay, I see no more hands raising. So let's move to Python implementation and see trimming and capping, how we can do it in Jupyter. All right. So first, we'll be seeing how to do trimming. And for the same, I have taken Boston House dataset for reference. The first step always is we will be importing the necessary libraries. So we're importing pandas and numpy, and we are importing matplotlib and cbun for visualization purpose. We are importing stats from scipy.stats for QQ plots so that we get to understand the distribution of the data as well. And we will be importing the Boston House dataset from sklearns.dataset. And this is for just ignoring the warnings. Okay, we'll be executing this. Fine. For Boston dataset, we will not be exploring all the features. We have only taken 3 features. One of it is RM, LSTAT, and CRIM. And they all are continuous numerical variables. So we'll be taking only these 3 features from the dataset. So the dataset Boston looks like this now. Okay. And if you see the shape of it, we have around 506 rows. So that much is the shape, or that as much as the size of our data set as well, with 3 different columns. Next, I have created a function which is called as diagnostic plots, which takes the data set and the variable which we want to plot different plots for. So the first plot that we'll get is a histogram. The second one is the QQ plot, and the third is box plot. So in here, we just have to call this function and we can get the visualization of all these plots instantly using this function. So this is a function that I've created. And then we'll call the function with the first variable RM. So if you see RM, it looks a bit of a normally distributed. If you see here the QQ plot also, there is some distortions present if you see the tails of it. So we can see that some distortions are there. This can be due to the presence of outliers. And if you see the box plot, in this range in the upper part as well as in the lower part, there are lots of outliers being seen. Okay, this is for RM variable. Another one is LSTAT. Here also, if you look at the histogram, you can see that there is some skewness present. Okay, it looks to be positively skewed or right skewed data set. The QQ plots is also showing us the same information that positive skewness is being observed. And if you see the box plot also, here if you see there are lots of outliers present on the upper side of the data distribution. We will similarly analyze another feature named as CRIM. If you see the histogram, it looks like it is extremely skewed towards the positive side. If you see the QQ plot, you can see that the positive skewness can be visualized very easily. And the box plot of it represents a lot of data considered or detected as an outlier by the plot. So we will apply the trimming method, which is removing the outliers from the data set for these variables. Okay. If you see about this box plot for RM, you can visualize that outliers are present in both the ends of the box plot. In case of LSTAT, it is only present on the upper side of it. Okay. So this can be because of these outliers, the distribution of our data is also skewed because of the presence of outliers. As we have already mentioned, presence of outliers is one of the reasons why our data set gets the skewness or they get distorted, right? But it is not necessarily that only skewness represents the presence of outliers. If you see here, this distribution with the histogram is saying that it's somewhat normally distributed, but if you check the QQ plot and the box plot, you will get a clear, fair, pretty idea about the presence of outliers in both the tails. Okay, so we will also always have to check for box plots to understand the presence of outliers, and we usually plot histogram and QQ plot to understand the distribution of our data. Okay. For handling them using trimming method, I have created another function which is find skewed boundaries, which takes the data frame, the variable which needs to be handled, and the distance over here. Okay, so we'll be using the IQR method, the IQR rule, to detect the outliers here. So first we have calculated the IQR, which is interquartile range. So I have taken a difference of the 75th quantile with 25th quantile, that is Q3 minus Q1 I've done here. And then I have figured out what is the lower boundary and the upper boundary for this variable using the IQR rule, which is the quartile 1 minus IQR into distance. So this distance is usually 1.5. If you are wanting to detect the extreme outliers, you can replace this distance with 3 also. But usually we take 1.5. So this distance can be also regulated because we have put that as a parameter over here in the function. Similarly, I have calculated upper boundary here. So that is the Q3 plus RQR into distance, the usual RQR formula that we have seen in detection, right? And then this function is returning the upper boundary and the lower boundary. So when we apply this function to a variable, what we get is the upper boundary and lower boundary. So any value which is present beyond upper boundary, in the higher range of the upper boundary, they will get removed. And the values that are present below the lower boundary, which is less than the lower boundary, will be trimmed or will get removed. Okay. So firstly, we will be calculating the upper limit or the upper boundary and lower boundary for the variable Rm. If you look over here, Rm has a lot of outliers present in the upper range and the lower range, both of them. So we'll be removing all of that. In case of LSTAT, we see that a lot of outliers are present over here. That will also get trimmed. And in this case, CRIM variable, a lot of variables I can see are present in the upper range. So that will also get removed. So here, using first find skewed boundaries, the function that we just have discussed, I'll put the dataset name Rn, which is the feature, which is the variable that we'll have to detect the limit for, and the distance, which is this distance, I've put it as 1.5. Accordingly, it will return us the upper and lower limit like this. Similarly, I've applied for LSTAT and for CRIM. We are getting the upper limits and lower limits. Then the next, in this code cell, what I've done is I have flagged them. Flagged them means I've just marked them because I want to remove them. So I'm flagging all the outliers based on this upper limit and lower limit information that we have got. So for that, I have used numpy.where function. Okay. For Rm variable, first, what are we doing? We are first checking that in Boston Rm feature, whichever values which are greater than the upper limit, flag them as true. Okay. And if they are not greater than the upper limit, then in that case, if they are less than Rm lower limit, then flag them as true. And rest all the values, please flag them as false. This is what the code explanation for and an easy understanding of what this code is doing. I'll repeat it again. So np.where is it is detecting outliers. Okay. So in the Boston Rm variable, whichever values which are greater than the upper limit that we have got from the function already, if they are greater than the upper limit, please flag them as true. And if they are not greater than the upper limit, then please check whether they are less than the Rm lower limit. If they are, then please flag them as true. And rest all the values, please flag them as false. So the values that are flagged as true will automatically be removed in the later stages. And the ones that have been flagged as false will remain in the feature as it is. Or in short, the ones that have been flagged true are the outliers. Similarly, I have detected or flagged those outliers for LSTAT as well as CRIM feature. For all these features, I have flagged them, all of them. And altogether in the Boston dataset, I have detected them, which are not the outliers. I have detected all of them. And then I have saved it in another dataset called as Boston trimmed. Okay. So I've created another dataset which does not contain these outlier values. So I have basically removed them from the outlier. I've completely created another data frame without these outliers values. Okay. If we compare the shapes of both these data frames, Boston is the data frame containing the outliers and Boston trimmed are the ones which does not contain the outliers. If you look at the shape of it, we have lost almost 100 rows. In total of 500, we have almost lost 20% of our data, right? So this is one of the reasons why we don't go for trimming much in machine learning, because it tends to remove a lot of information from our data set. Okay, if you have only lesser amount of outliers present, then we can certainly use this method. Otherwise, this is not suggested. Let's also see what kind of effect it has done in the distribution of the data. So after trimming, if you check the RM feature, well, it has, yes, not much distorted the distribution. In fact, it has now decreased the skewness of the data set a lot. If you compare this of RM with respect to what RM QQ plot looked like previously, if you see here, the effect of outliers in both the tails was easily being seen. But now here, after trimming, you can see that the outliers are not anymore distorting the distribution of the data. And the box plot is also not reflecting a lot of outliers. Well, certainly after removing the outliers, the data set that we have, again, if you plot the box plot, some outliers will automatically be detected. It happens because it keeps on updating the values. So this much is still okay. But if you go for LSTAT, in case of LSTAT, even though we have removed the outliers, the distribution doesn't seem to be very normal. Well, it has not changed the, it has not changed the, or it has not recovered the distribution or the normal distribution back. You can see that it's still a bit skewed, okay? And the box plot still represents a lot of outliers because they were present in a huge number. That's also one of the reasons. In case of Boston trim dataset, we are checking for CRIM variable. Well, you can see that the distribution is still not normal. And after the recalculation of the parameters, it still is detecting the values in the outlier range. Okay. The main reason why the trimming has not worked in LSTAT and CRIM is also because of the percentage of the outliers present was huge in number. So trimming did not work that well. So probably if you occur these kind of scenarios, you can use capping technique. But then capping, if you're using for a lot of number of outliers, then you'll have to switch to a non-linear model, or you can use a tree-based algorithm for that, because it will even more distort the distribution of the data. If you're going for linear models, then I think you'll have to settle for this. Okay. The next technique is capping. In capping also, we'll see two different detection techniques. First is interquartile range proximity rule. We'll detect the outliers and we'll handle them. And the second is using quantiles technique. We'll detect them and we'll handle them. Let's first see how we can cap the outliers using interquartile range proximity rule. Okay. I've taken the same data set. I've just added one more, that is MED-V to it. I've taken the same data set for reference. And I've used the same function which we have defined previously for diagnostics. We have already defined it in the first section. I've used that for drawing the histogram, QQ plot, and box plots, respectively. In case of this, I'm detecting the outliers using the same fine skewed boundaries using interquartile range only. Instead of trimming it, instead of removing it, what I'll be doing here, I'll be using the capping technique for handling it. In the first section, we remove those outliers, but here we will be using a capping technique. So this function first we will use to detect the outliers, or detecting the lower boundary and upper boundary respectively. Then we will get the lower and upper boundary for RM upper limit and RM lower limit, that is for the feature RM, we will get it. We will keep 1.5 as a distance again over here. Instead of removing, what are we doing here? Let's see that. So the new, after replacement, what we are doing is we are updating the RM feature where the Boston RM, the feature RM is greater than the upper limit. Previously, we were flagging them, the outliers, but now we are replacing them with the upper limit, which is called as capping. So whichever values that are present beyond upper limit, which are greater than the upper limit, they will be capped as upper limit only. The values will be replaced by the upper limit. And if they does not satisfy this condition, then we are checking for another condition where if they are less than the lower limit, If the values or outliers are present which are lesser than the lower limit, they will be replaced by the lower limit itself. Okay. This is how we can use the capping technique. So instead of flagging the outliers and trimming them out of the data set, we are replacing them with the upper limit and lower limit. Let's see what kind of effect it generates in the data distribution. So here, if you see, a spike is observed in the lower end and the upper end of the data set. Why? Because all the outliers have been capped as the upper limit over here, and over here also all of them have been capped in the lower section. Let's compare this with the previous distribution. See over here, the outliers have been added here in the upper range of it, the upper boundary, and the outliers here have been added as the lower range or the lower boundary. So that is the reason that you see the distortions in the normal distribution can be observed in the upper part and the lower part of the data. So if it is getting distorted, certainly you can reflect it in the QQ plot also. If you see both the tails, it is representing the presence of outliers, or will we see that there is a distortion present in the data. But if you check for box plot, well, finally we have removed all the outliers. It is not reflecting anyone. But the major drawback of this capping technique is that you will or we will get a distortions in our data set. The capping works well when we are using any tree-based algorithms, but if we're going for any linear models, then capping may distort even more the data set. So we'll have to take care about that. We'll have to visualize for all the variables in which we are engineering our outliers using capping technique. Okay. Any questions till now? Okay. Let's also see the capping with quantiles. So here we have used the IQR range for detecting the outliers first. Now we are checking the quantiles method to detect the outliers. So similarly, I've taken the same data set and using the same function, I'm plotting the histograms, QQ plot and box plots. We can see outliers present in both the ends. Now we have created another function which says find boundaries, which is using the quantile techniques. So if you recall the quantile techniques, let me show you. Yes, quantile techniques, it marks the upper limit and lower limit as the 5th quantile and 95th quantile. So lower limit, which means that 5th quantile is the lower limit. Any value which is present beyond this 5th quantile is detected as outliers. Any value which is present beyond 95th quantile is represented as an outlier. Okay. This is what this function is doing. It is calculating lower boundary with, or it is marking the lower boundary as the 5th quantile and upper boundary as the 95th quantile. This is what it returns also. And we will apply this function to the RM variable. Here we'll be finding the boundaries. Okay, so we get the upper limit and lower limit of the variable RM. Similarly here also. And here we will be using capping technique again, as previously we done for the IQR technique. The same way we'll be doing it for quantile technique. The same code it will be. So wherever you see if the variable data is greater than the upper limit, you replace that value with the upper limit. If it is less than the lower limit, then you replace that value with the lower limit. Like that, we are performing capping technique as well. And let's see how it has reflected in the distribution in the histogram. If you see, because of that, a huge integration of data you can see in the upper part, or in the 95th quantile value, you can see a huge data aggregation. And similarly, in the 5th quantile range also, you can see a lot of data has been aggregated because all the outliers have been now replaced with the 5th quantile and the 95th quantile value respectively. And that same kind of distortion will be also reflected in the QQ plot. If you see here, the distortion has been marked in both the tails of it. But we could handle the outliers. Now box plot is not reflecting the presence of outliers anymore. As discussed, capping and trimming both can be used, but we would prefer capping more in terms of handling the outliers engineering. The only drawback that we have to check for is that it distorts the normal distribution. Okay. But then if we are going for linear model, one of the other approach that we can do is we can apply outlier engineering using capping. And we can then furthermore, we can transform the data set into normal distribution using different transformation techniques. So that can also be one of the approach if we are going for linear models. If you're using any tree-based models, no further transformation technique needs to be applied. But outliers certainly, if in case they are present, it's always suggested that we should always handle them. Okay. Any questions here in these three techniques, in these three methods for handling outliers? Anywhere, if you're not able to understand the code or anything, please let me know.